I'm Henry Stapp. I'm a quantum physicist. I've been working at Lawrence Berkeley Laboratory of the University of California for many years. I worked with Pauli and with Heisenberg and with John Wheeler, so I've been at this business for a long time. I wrote an essay called Mind, Matter, and Quantum Mechanics in 1958. So I've been thinking about this problem for a long time.
Since I was 4 years old, in fact. It's very impressive. First of all, I'm John Hagelin, a quantum physicist, a string theorist, unified field theorist, fundamentally interested in consciousness and higher states of consciousness. And I just can't resist adding, and for those who may not know, that Professor Stapp, Henry Stapp, is a highly distinguished and revered professor contributor to quantum mechanics with a very clear mind, formulating areas of understanding that are intrinsically quite abstract, and has done a lot to clarify the whole interpretation of quantum mechanics and continues to make a very strong contribution even today.
Well, thank you.
And I think the interest really of our audience is largely going to be to try to get some clarity on, well, the wave function we probably have heard a bit about, and even entanglement, but maybe the most mysterious aspect of the whole thing is the collapse of the wave function. There are a variety of points of view that the environment does it, decoherence does it. I don't fundamentally agree with that point of view. So maybe you could just describe for us, what we mean by the collapse of the wave function, and possibly, why it happens.
Well, the first thing to appreciate is the ontological character of the wave function. It's not a description of a material universe at all. It's a description of something called potentialities. Yeah. So potentialities are kind of a realm of possibilities. They're more in the middle realm. Okay. And they describe possibilities, and these are possibilities for experiences. The way quantum mechanics works is you have a very important role is played by observers. And observers ask questions about what their experiences are going to be, and nature answers yes or no to a question posed by the observer about what his experience is going to be. So the whole thing is lodged in the realm of experience to begin with. And this state of this quantum state, which is the physically described aspect of the observer's awareness and experience, is because it's physically described, there's a tendency for people to think that it's material, matter-like, but that's not the case. It has this quality of being what's called Aristotelian potentia. That's a possibility for what your experience might be. And so the observer asks the question, is my experience going to be such and such? And this is immediately answered by nature, yes or no, your experience will be the one you just described. And this is lodged into the ontological reality in what's called the wave function. And if the question is about, in particular, about the physical world, am I seeing a desk there that has a green top? And then your answer will be lodged, this experience has occurred, and the physical description of the universe collapses to a form that's compatible with nature's answer to the question. So I ask a question, will my experience be such and such? Nature answers yes or no according to certain probabilistic rules that quantum mechanics provides. And say if the answer is yes, then nature collapses the original state, the state of the universe that was there, to a new form which is compatible with the answer that nature has just given to your question. So it has to do with the nature, it has to do with this potential character of that is called the quantum state.
Mm-hmm. That's actually very beautiful, very complete. That's a rather comprehensive answer. And maybe we could unpack it just a little bit. One thing you said I absolutely love and would totally support, and that is that the wave function is not what you'd really call a material thing. It really exists more on the level of mind, the mental world. If you ask a physicist, what is a wave function, they probably would think about it and they'd say, well, actually, it's a vector in a linear space, a linear Hilbert space. And you ask, well, what's that? Well, what is a vector in a linear space? Well, it's a concept. The wave function really is kind of made of the same stuff that mind is made of. So I don't know if you agree with that.
Yes, I do.
Okay. And so interestingly, we have this on the level of mind, the interplay of possibilities, the interaction of potentialities, all on the level of quantum mechanics. And within that sphere, possibilities arise. For example, possible answers to the question, is the desktop green? Or is it red, perhaps? Or is the desk here? Or is it slightly shifted over there? The wave function embodies those possibilities, but when the question is asked and a measurement is performed, the collapse occurs.
Yes. Nature delivers an answer to the question, is the way it's formed. So you have two players here. One is the whole body of observers. All human beings, for example, are regarded as observers who can ask this sort of question, make observations, and then there's this other player in the game, nature, which delivers an answer. But the main thing, being the one you've already stressed, is that the whole thing is existing in a mental realm. Maybe I can just expand upon that just a bit. It was discovered early in the 20th century that the old-fashioned classical mechanics, which was a deterministic universe made of matter that couldn't move faster than the speed of light, for example. And so you had this very rigid matter-based idea of what the world was like, and also what science was like. Science was regarded as something that had to do with these physical descriptions, and mind was left completely out of the picture. Well, it didn't work when you went down to the level of atomic phenomena, and the scientists who invented quantum theory shifted viewpoint. They said, well, what really exists, the only thing we really know exists, is our own experience. Our experience, and if we're human beings, we can communicate our experience. So there's something called our knowledge that plays an important role in the description of quantum theory. There's our knowledge, which is an objective thing, but it's made up of the knowledge of all of the individual peoples. So this is the objective reality of quantum theory, and it's knowledge-based. Now, as you know, in philosophy, there's something called epistemology, which is about knowledge. There's also something called ontology, which is about what really exists. And the core move, you might say, of the invention of quantum theory was to unify these things. So instead of having epistemology and ontology being two different things, they became the same thing because the things that really existed were our knowledge. So you resolve this fundamental problem in philosophy of how to get these two things that seem so different together. The key move in quantum theory was basically to put those two things together and make them one.
Yeah, that's a beautiful perspective. And then pursuing the line of discussion of a moment ago, this wave function of the universe is a wave function of the system in this case, the wave function that describes the desk, for example, is evolving in a certain way, which would, has a certain probability, you could say, of the desk being in place A versus place B. And we pose the question, which is it? And nature responds with an answer. It's kind of interesting because nature presumably set up those probability rules to begin with, the rules of quantum mechanics. And nature, exerting a certain amount of free will, free choice of some kind, and giving us an answer to that, is playing by those very rules. Because if quantum mechanics says the green top should be there approximately 50% of the time, well, that's what you're going to find. So we have a set of rules provided, presumably given to us by natural law, by nature. And an answer, you could say, an outcome of a measurement, which will satisfy those probabilistic rules. And the question, I guess, is it? Do you have a feeling about this? Is that outcome of the wave function, the green top desk on the left versus inched over a bit to the right, is that a random outcome? It certainly seems to be often considered to be so in physics or from the perspective of the observer. But with respect to nature, is there a rhyme or reason to it, or is it the roll of a dice?
Well, let me answer by first saying that as far as the choice on the part of the observer is concerned, there is no probabilistic law there. It's called the free choice on the part of the observer. So as far as the observer is concerned, we don't have this statistical rule that's governing it or limiting it in any way. So to get to your question about how about nature's response, now the primary rule in quantum mechanics is that this response is supposed to be random. Now, what random means to a mathematician or a physicist is that the probabilities have a certain weight. It might be 30, 70, 30% of the time. If we do a long string of experiments, 30% of the time it'll be yes and 70% no. It doesn't mean necessarily equal probabilities. It's some specified fraction which is determined by the mechanics of quantum mechanics. There are rules to establish what those probabilities are. Now, the rule, quantum mechanics specifically says, and that's the end of it. This choice is random, statistical, and we should not go any further. Now, but there is the question of what's the reality? I mean, is it really true that it's just plucked out of nowhere? Now, I find that idea that really something is determined by nothing at all to be too irrational for me to accept as
you and I and Einstein for that point. For that
as a final answer.
That's right.
But I think the particular rules that quantum mechanics provides are based and are essentially a quantum mechanical expression of what in classical mechanics is a well-defined and well-understood principle. It's called equal volumes of phase space have equal likelihood to occur. And there's a long history of going why that's reasonable, and it works very well in all of physics, which deals with probabilities. So it's the quantum mechanical explanation or interpretation of that probability rule. But all that it means then is that insofar as the only things that are determining the answer are somehow the physical description, if the only things that are contributing to the probabilities have to do with physics alone and the possible physical possibilities, then it makes sense that the probabilities should be such and such. However, we've just been talking about the fact that in quantum mechanics, mind is playing a role. Mind is actually asking questions. And so if indeed nature is paying any attention to mind, then you might even expect the answers to be, well, they might depend on mind. They're not coming out of nowhere. They're depending upon mind. And but when you average over all the many experiments, the idea is that this washes out. If everything only depends, if things, well, let me say it this way. If things only depend on the physical, then what you expect is that these would be the probabilities, even if there is an actual rule that says why it's this way. Nonetheless, averaging over many experiments, you expect that to average out. On the other hand, if mind enters in, then that's still another dimension why it's not purely, really random. But I think we agree that, I get the impression that the idea that just comes out of nothing at all is something I'd rather not believe.
And I would rather not believe that. And Einstein, of course, was so vitally against that that was probably the principal reason he never really bought into quantum mechanics. But if you could, I suppose, and this is perhaps where the physics stops, and the level of individual interpretation at this point, which is still a very much evolving thing it's a very active area of dispute, not dispute, but certainly lively debate within the physics community and physics consciousness community. If you could attribute possibly to nature, who is somehow making these choices, and how those choices are made are certainly beyond the mechanistic calculational capability of quantum mechanics, then maybe there is some will of nature or mind of nature involved. And at that point, quantum mechanics really doesn't quite say for sure. Very interesting. So let me ask, so this is an extremely clear elucidation of what has slowly emerged as, I'd say, the mainstream or orthodox view of quantum mechanics. It certainly leaves areas of discussion that are still lively, probably need to be pursued. And one we talked about for a moment just prior to our interview today, and that would be, well, okay, so human beings constitute conscious observers. A human being, and we must make these observations continuously. I mean, whether the table may have evolved into a state of A versus B to a small extent while we were out having lunch. And just a casual glance across the room, once we notice where it is, we have made a measurement without putting a whole lot of forethought into it. What if sitting in this chair right now, instead of me, were a chimpanzee, which I'd like to argue that is a little different from me in some respects. But if I were a chimpanzee and cast my glance around the room, I'm just anthropomorphizing perhaps, but I would assume the chimpanzee is noticing the table over there, not over there. And if that's true, that might imply that the chimpanzee could substitute for a human being in this context, just perhaps by way of reasonable discussion. I don't think we know that, but would you agree with that, or not sure?
Well, that is one of, I would say, an open question. What constitutes observers? What class of entities are observers? And the way quantum mechanics originated, it was a scientific methodology for scientists to make predictions on the basis of what they know for what might happen in the future, statistical predictions about the future. So in that narrow context, the only people that really mattered were the scientists, as a matter of fact. Well, let's expand that at least to the whole human race, because we are a group of communicating observers. We all are observing. We can communicate with each other. I can tell you what I've done. And so I think most people would agree we should at least expand it, say that the observers include normal human beings. Now, I think it's too anthropological that it seems to me we should maybe expand at least to biological systems, all biological systems, even very simple unicellular things would have some measure of observership. They would be able to enter into the dynamics in this way. Of course, an amoeba or something is not going to be very effective, but it wouldn't go down to a thermostat, which also makes decisions. It gets some input and it does things and causes things to happen. But at least from my point of view, I would rather say no, they're not conscious, and but it's certainly not anything that's written in stone. So it's something that's not clearly answered in quantum mechanics.
Right. It's interesting, for a little bit of further discussion, if the table were actually a piece of cheese which had moved into two locations at once, a quantum superposition of both locations, we walk into the room, we have a glance, we know where the cheese is, that wave function has collapsed. If you want to use a mouse instead, who's going to be quite interested in that cheese, will probably wander over and take a bite, you would think that if the mouse constitutes an observer, which we haven't settled, but if it does, the cheese is now in one spot. so that which the mouse has located and is now devouring it. If a mouse is not an observer and is not enough to collapse the wave function, then probably you have a mouse devouring the cheese on the left and a quantum superposition of the same mouse devouring the cheese on the right. So then the mouse, like Schrodinger's cat, would be, existing in two places at once, so to speak. And that's certainly very intriguing. And then,
it's existing in two places at once, but remember, this is in the wave function.
Right.
And what the wave function is potentialities for experiences by observers. So there's no contradiction anyway here. Yes, the mouse and the cheese and the live and the dead cat are, if the cat's not conscious.
If the cat's not an observer.
If the cat is not an observer, there would still be this superposition of possibilities for what observers would see if they looked.
That's right. All right, well, I want to follow that up with a lot of discussion at this conference on decoherence, a few talks anyway that have talked about it, I don't think correctly. I would imagine you would agree that the perturbing effect of the environment, you have to be a little more careful about it, would take more time, but I'll just shorthand by saying the sort of randomizing influence of thermal effects and background photons in the environment might be enough to collapse the desk with the green top as being not here and here, but simply being here. Now this is something that we think a conscious observer would do. And I agree that we certainly must do that. In the absence of any observer, except for the randomizing influence of light in the room, there are quite a few people claiming, and I don't think it's mathematically sound, that perhaps the perturbing of the quantum correlation between the two possibilities of the desk, which might, because of the washing away, in a sense, of the entanglement between the two positions of the desk, could perhaps lead to somewhat of an independence of those two options. But the disappearance of one option in the place of the other, which we would assume to be the result of the collapse of the wave function. I don't see how that happens. I don't think I believe that happens just as a result of environmental decoherence. And you're quite an expert on this subject. I'd love to hear your thoughts.
Well, I completely agree. If you look at quantum mechanics, there's no question. The effect of the environment does not collapse the wave function to one form or the other as an observation by an observer. Observers play this special role, only they can collapse. Now, it is true that there is an effect on this. We have the two mice and the different eating, and there's something that's a little technical. It's called a superposition, and a superposition means that you can bring these wave functions back together and they interfere with each other.
Right.
And the effect of the environment is to change that combination to something called a mixture. And so this is a big distinction in quantum mechanics, a distinction between a superposition, which means you can bring them back together and they interfere, and a mixture. If they're a mixture, then you bring them back together, and it's just like adding the two possibilities independently. Right. Now, there's no cancellation like there can be when you have a superposition. So I think it's absolutely clear that in quantum mechanics, orthodox quantum mechanics, the effect of the environment is to change the superposition to a mixture, but they're both still there. They have not collapsed the wave function. It's very different from what an observer, one of these quantum observers would do.
I have an ally in Henry Stapp. I just want to make that very clear here. Yes, exactly. The quantum mechanics, that's what it tells you.
Yeah, no question.
Anything beyond that, it's a big leap of faith. And I tell you, the reason I think that there are a lot of people who are not necessarily deeply versed in quantum mechanics, who would assume that perhaps what you're getting in that case is a collapse of the wave function. Unless you're familiar with the density matrix formulation of quantum mechanics, and you're stuck with maybe an undergraduate treatment of the subject in which you've got state vectors or wave functions, but you don't have the density matrix, which is a more generalized way of formulating the whole theory. If you don't have that, which is studied maybe, later in one's graduate education, if at all. And you have to be somewhat of a specialist to do that.
Well, that's why it's so important. I mean, von Neumann was the one
Right.
who took the Copenhagen interpretation, which was not quite mathematically formulated, and one of his main contributions was saying the state of a system should not be represented by a wave function. It should be represented in this other different mathematical form as a density matrix. And so it's mathematically a different sort of structure, and it can have within it the possibility of mixtures. In other words, in this case, the two elements, the two mice, are combined, and they're into what is called a mixture. This full state is now in a mixed state, which means that once you bring the two back together and let them overlap, it acts as if they were just adding, say, 50-50, one with the other, and all of your observations will be as if it was 50% here and 50% here, independently of each other.
Exactly. The other part you've brought in is I think even more richly nuanced, and that is the role of the individual observer in posing the question of nature. A certain amount of freedom that we certainly feels like we have to make decisions about what we want to measure in quantum mechanics. One thing we haven't really gone into is there's a certain amount of freedom in what you choose to observe. It may not be so obvious from the case of the desk, but if you want to look at the spin of a particle, which might be spinning up versus down, or more likely a quantum superposition or correlated coexistence of up and down, that is a choice you can set up, and you can measure to determine the outcome of which is true. In the process, collapse the wave function, because probably both were true, and after the measurement, only one is true. But you could have also decided you were interested not in the up-down dimension of spin, but you could have also decided, I want to measure the horizontal component of spin, whether it's left or right. Most likely it is in a state of both. And after you make that measurement, it's going to end up either left or right, just as before it would have ended up or down. Those are two rather different sets of choices you've posed to nature. And in both cases, you're essentially leaving nature the freedom, the option to choose which is which. But the point you often make is that the initial choice is ours, whether we want to decide to measure the vertical axis of spin or the horizontal axis of spin. And we may have good reasons for choosing one over the other, but it is a choice we make. And that's, maybe you want to comment on that, and we could pursue that just a bit before I know we have to wrap up.
Yes, and the question your implicit question is, how is that choice made? I mean, where does it come from? And it involves a little bit of explanation, detailed. The point is, we feel that we are individuals, and we kind of feel a history behind us. And so what is it? Well, in our past experience, we've made these choices of, am I going to see this, and such happens. So there's a residue of understanding, if I do this, this will happen. And if I do this, this will happen. So this feeling you all have of somehow having an existence, we have a feeling that for all of these, you might say all of these experiences that we had have kind of melded together to give a feeling of usness that involves all these ideas of, if I do this, this will happen, if I do that. So it makes your choices meaningful.
An informed choice, so to speak.
They're informed choices. They're informed by all your past experiences of what has happened in the past. So you exist not as just something that's here and now. You exist as a consequence and a product of all these life experiences that you've had in the past. And that gives you the feeling of being you, because that feeling is somehow a feeling, I know how to do things. I know if I want this to happen. So you have this whole feeling of you-ness, and also the experiences that you've had about gaining knowledge. So you have a huge, rich kind of semi-conscious, almost unconscious knowledge of who you are, and upon which meaning can be based. In other words, you can, once you understand yourself as somebody that has these capacities, you can form values. Some things worked better, some things worked worse. Mm-hmm. So you can embed in yourself values of this is good, this is bad. So you have this conglomeration of feelings that constitute your mental, your psychic being. And so it's on the basis of those feelings of you, who you are, what you value, that the choice is made. It just doesn't come out. It's what Bohr calls it, the free choice on the part of the experimenter. That's one of the phrases that is, and he also talks about, the free choice on the part of the experimenter. But this free, you have to break down what free will or free will choices means. And what it means in quantum mechanics is that these choices are not determined by the physical variables. They're not determined by the physical aspect of nature. In other words, that means the only other thing we know about is the mental.
Right.
It says the mental is coming in here, and by the mental, I'm talking about all the things I just talked about. The feeling of who you are, what your values are, your capacity to do things, what sort of effort to make in order to cause something to happen. So the you that is behind these choices is this complex you that I'm talking about, all derived basically from your past experiences. And so these choices are meaningful. You've injected meaning into the universe because you have these values, and you're an individual that has the capacity to make choices to implement one value and de-emphasize another value. So these free choices are not something that's coming out of the blue.
Sure.
They're not coming out of the physical world, but they are coming out of you as a mental being.
Well, that is fascinating, and this may take us beyond the time we have, but to sharpen the question further, given that, it certainly makes sense. But you would say, I would say, that the brain, which is, all the molecules and atoms and cells, are under the grip of, functioning under the action of the quantum mechanical dynamics, or just put it simply, the Schrödinger equation. And in our brains, certainly, they're shaped by our experience. They may, certainly probably the brain has a very important role in those experiences, how we see things, how we store memory, what memories are stored. There's a lot of brain stuff in all of that. So if that brain is more or less chugging along according to the Schrödinger equation, in which there's not a whole lot of freedom because the equation itself is deterministic, the mind that you're talking about with some freedom has to eventually influence that brain so that the brain goes about moving the arms and setting up the experiment to answer the question. So if we have something that is sort of a beyond physical, beyond quantum mechanics, let's say, or beyond at least the Schrödinger equation, level of mind, sort of beyond the physical level of mind, and not governed by the deterministic evolution of the wave function. It's very interesting, and I think we all sense that that's probably true. Do we have a sense at this point of how that mind has an influence on the brain so that the brain goes about its business? Is it just the same observer effect, that the mind itself, in a sense, becomes a kind of observer and thereby influences the brain in a sense that an observer would, which might be part a random response of the brain, or maybe more than just a random response of the brain? What's that interface?
Yeah, well, the important point here is that if you actually look at the brain and how it functions, a very important role is played by something called ion channels. Ion channels are huge molecules that have a little tunnel through them through which ions, calcium ions or potassium ions, can migrate. And it has a very narrow opening as it goes from outside the cell to inside the cell. There's a narrow opening, and the effect of that small physical side means that the velocity of the of the ion, calcium, as it comes out, is spread over a wide area. It's not just a little line. No, according to the uncertainty principle, it's spread out. So all of these ions, channels, are feeding ions into the thing, and they're spread out all over everything. So when you said the mind is just chugging along doing one thing, no. Suppose you're sitting in you're walking through the forest and out jumps a strange creature. Well, your mind is originally going to, depending on on how all these ions, these gels, is going to be able to create a number of different scenarios for what you might do, fight or flight. And so it's not that the brain has just one thing available. The brain is exhibiting...
Quantum mechanical. So it has coexistence, superposition.
It has a coexistence, superposition, or mixture maybe. Pretty much a mixture because of the way it goes. And so it has this mixture of all the possibilities. So the mind here is not just looking at a brain that's fixed. It's looking at this array of possibilities for what it might do.
Ripe for collapse.
You're ripe for collapse, right? It's ready to be collapsed. Where's it going to go? And now we have this mental entity that sees all these possibilities laid out. It has its values. It has its capacity to make things happen because of how it's learned to relate its efforts to how it acts. So it looks down and sees this array of possibilities, and on the basis of who you are, in that sense that I've just described, it makes its choice amongst these available possibilities.
Okay, so it's very interesting. And then, so we have this mind, which is really, very much us, a very essentially individualized mind. That individualized mind basically observes the brain and, causes collapse of the quantum wave function of the brain itself, which either sort of in the sense of a random outcome of the measurement, we could even talk about some steering of that through something like a Zeno effect, possibly, who knows. There's an influence, that is, whether the influence is relatively random or there's even a way of guiding that. And that's something, of course, we could discuss if we had unlimited time. The question that comes to my mind is, this mind that is basically an observer to the brain, it has its independent sense of self and maybe even memory and so forth, almost in a sense a little bit independent of the brain.
Mm-hmm.
Have you thought of what might constitute that type? It seems to be more than just an abstract intelligence, abstract observer. It's got almost personality. It's got memory. It's got meaning. So as a physicist, my first question is something I've talked about at this conference is, might there be a physics to that? What kind of physics? Is it quantum mechanics? Is it something beyond quantum mechanics? Is it made of normal matter? Is it made of something else, which string theory might suggest, a candidate for what it's made of? Have you had an opportunity to think about that mind that we sense we have, which is influencing our physical brain? Does it have its own dynamics? Does it have its own substance?
I'm sorry you said substance. In any case, dynamics, I would say absolutely yes. And that's what I've been trying to be talking about here. It is doing mental processing. So it is a mental entity.
So the mental processing a bit beyond the brain, though.
I know. I'm talking about the mind.
Yes.
I'm talking about not the brain.
Right.
The brain is doing this thing. It's generating possibilities.
Right.
But the mind is up here made of a different sort of stuff. The brain is described in physical terms. By physical terms, I mean it's described in terms of ascribing mathematical properties to space-time points. And on the other hand, we have this mind which is described in psychological terms. Sorrows, values, pains, sensations, a completely different language that's used up here. It's a different sort of entity from the brain, and it is examining the brain. It has this capacity it's attached to the brain, but you have to think of it either in mental terms, and some would prefer to even say in maybe spiritual type terms. I mean, there's this mind, body, spirit that we keep hearing about, and this distinction between mind and spirit, where you draw the line, I'm a little unclear about. But this mental part, whether you call it mental or spiritual, is different from the physical part, and it is acting upon, it is choosing on the basis of these considerations that we've been talking about. It's choosing which option that the brain is displaying to choose. So you have what some might choose to call a spiritual element, and others might just choose to call
the mental element.
Mind
Sure,
element.
sure, sure. Well, possibly a point of discussion for a future interview, because I know we have to wrap this up. You have a very busy afternoon. Is it strikes me then it would be inevitable for that kind of mind, if it's going to have an influence on our brain, even causing the wave function of the brain to collapse in certain respects. There's going to be some energy exchange. It may be tiny, it may be unmeasurable, in which case I wouldn't be so concerned about it, but it will be there. And that, as a particle physicist, opens up the possibility for me of certain types of experiments that might even attempt to detect a violation of energy associated with collapse of the wave function. Anyway, there's a lot we could think about and talk about. That interface between mind and brain is an important subject. And
Absolutely. And I think that's really, where my interest lies. I mean, this understanding of the mind-brain connection is what it's all about, as far as I can see. So it's a blending of neuroscience and physics and quantum physics in particular, and the question of experiments that will tell us something about more than we know at the present. So certainly tons of unanswered questions, and my efforts at the moment are closely connected with neuroscience that I'm talking about, and trying to formulate experiments that will shed some sort of light beyond this general framework that I've talked about.
Right. Some specifics need to be sharpened at this point.
Absolutely.
Well, thank you very, very much for sharing some time with me. It's
well,
a great
thank you
honor and pleasure for me to talk with you.
Thank you for wonderful questions.
And thanks for being at the conference this year.
Oh, thank you.